Hey guys, today we're going to talk about current and how current flows. Not a day goes by that you do not use electricity, whether it's in the form of your cell phone, lights in your house, your computer, or your TV. You always use electricity during your life. But do you actually understand what electricity is? Electricity is the flow of free electrons through a wire. This flow of electrons is called current, and it's measured in amps. So electricity is the ability for electrons to transfer energy to an appliance or a substance. Current can be compared to a river. The river will always flow from high locations to low locations. Just like that, the electrons flow from a high electric potential to a low electric potential. And electric potential values can be determined based on how the point charge reacts to being there. Now, that might not make a lot of sense right now, but we're going to elaborate on that on the next slide. So current is like a river. You always go from the high to the low, and it's based on how the point charge reacts to being placed in a location. When talking about electricity, point charges are used, and at the very top of this page, we have a point charge present. We used to believe that charges automatically carried a positive charge. So if I were to place a second positive point charge at this location right next to this other positive point charge, those two items want to be apart from each other. Opposite charges attract and like charges repel. So this would be considered an area of high potential energy. This point charge does not want to be here. So he is going to move in this direction, and he might end up over here. And this is considered an area of low potential energy. This point charge is happy. He's pretty far away from this other like-charged point. Okay? When we speak about the electric fields, we do this based on how a positive charge will react. Positives do not want to be near other positives, so that would be considered a high electric potential. But we later found out that current is not based on the flow of positive charged items. The protons can't move. The things that can move are the electrons. Those are in the electron shell, and they're able to actually transfer and move throughout materials. So we actually found out that current flows through wires based on those negative charges. So in this picture at the bottom, this is the positive terminal of a battery and the negative terminal of a battery. And when we place our positive point charge here, this would be a high electric potential because he really doesn't want to be next to the positive charge. So the flow of positive charge would be running away from that positive terminal, going through the wire, and hanging out next to the negative terminal. That would make him happy. This would be considered a low area of electric potential. But the flow of electrons is the exact opposite, because the electrons have a negative charge, so when they're here, they really don't want to be next to this negative end of the battery, and they would move across to the other side. So it's really confusing because electric potential is based on positive charge, but current is based on the flow of negatively charged items. Speaking of batteries, how does a battery work? A battery actually provides energy, so a positive charge can move through the battery. Positive charges are all hanging out at this end, this negative end of the battery terminal. And when we do work, this positive charge is forced to come to this location next to the positive terminal. Since it's sitting here, it does not want to stay there, so it continues moving out of the battery, down the wire, through the light bulb, all the way back to the battery, and it's happy again. But the battery goes, you're gonna move to this side, and it's unhappy again, moves through the wire, through the light bulb, back to the battery. And eventually this just keeps happening over and over and over and over again. So these positive charges have work done on them by the battery, and that's actually chemically based work. So this chemical reaction moves those positive charges from the negative terminal to the positive terminal. They get there and they're unhappy, so they leave the battery, travel through the wire to whatever the appliance is, back to the battery where it happens all over again. Now, this is happening with millions of electrons or point charges at a time. And since that is occurring one after another, after another, after another, it creates this continuous flow of electricity. And that continuous flow of electricity powers this light bulb. But the one thing you have to take into consideration is that wires are just like hallways. If you have a teeny, teeny, tiny, skinny hallway, only one person can move through at a time. So as this positive charge moves through the wire and gets to the light bulb, he drops off all that energy from all that work that was done to him at the light bulb. He keeps moving because there's all these electrons or all these charges behind him that want to get to that light bulb. So he keeps going through the circuit back to the battery until he can power back up again. So we'll talk about this in class if we need to, but batteries, you are forcing a charge to be where it doesn't want to be. It travels through the battery, it travels through the wire and goes back to where it's happy, then it's forced to travel through the battery again. So this idea of this transferring of energy, this is called current. With electricity, current is a measure of the amount of charge transferred over a period of time. It's a flow of electrons or individual negative charges. When the charge flows, it carries energy that can be used to do work in an appliance or in a circuit. So this equation is capital I equals Q divided by T. And capital I is current, and it is measured in amps. Q is charge, and it's measured in coulombs. And T is time, and it's measured in seconds. So what we're going to do is calculate either how much current is traveling or how many individual charges are traveling. So first practice problem. Determine the amount of time an LED nightlight with a current of 0.0042 amps would have to be used before 1 times 10 to the 6 coulombs of charge passes through them. So I'm going to write down my equation. I equals Q over T, and I'm going to list my knowns and unknowns. I is 0.0042, Q is 1 times 10 to the 6, and T is my question mark. So when I plug this in, 0.0042 equals 1 times 10 to the 6 over T. Now math law states I have to get this T out of the bottom of the fraction bar. I can multiply both sides by T, and then I would divide this side by the 0.0042. In actuality, I just switched places of the T and the 0.0042. So my T value is 2.38 times 10 to the 8 seconds. Now that's a huge number, so I'm going to go ahead and convert that to hours. I'm going to divide this number by 3,600, and that's the same as 66,137.56 hours. That LED nightlight would have to be on for a huge amount of time before 1 million coulombs of charge passed through them. Second practice problem. A large window air conditioner draws 11 amps of current. Determine the amount or quantity of charge that passes through the conditioner during an 8-hour shift. So I have I equals Q over T, I, Q, and T. T is 8 hours given to us, and I is 11 amps given to us. Q is our question mark. Since our equation needs time in seconds, I'm actually going to convert this. So 8 hours over 1 hour on the bottom, and 3,600 seconds on the top. That is the same as 28,800 seconds. So I have 11 equals Q over 28,800 seconds. I'm going to multiply those two numbers together, and my final answer is Q equals 316,800 coulombs. Okay, so we're going to practice with calculating current, coulombs, or time with this equation. Then we're going to take it a step further and actually start dealing with circuits. So this is the last mini step before introducing circuitry and how current travels through a circuit. So I'll see you in class so we can practice with this before moving forward.